All right. One of the most important things about vectors is being able to convert back and forth between rectangular and polar form. Don't get intimidated, but this is the thing that actually turns vectors into something useful. So in real life, we rarely ever think about things in terms of 3, 4. In fact, the only example that I can really think of that breaks things up into like strictly horizontal and strictly vertical movements is some of the games that we play, like chess. Like everything is very clearly a vertical or a horizontal movement. Checkers is kind of like that. Everything is like diagonal one space, or if you jump, it's diagonal two spaces. Most of real life is not nearly as clear cut in terms of moving left and right, moving up and down. Most of it you just point in a direction and you go that way. And in fact, a lot of it even involves curves, which is like what we use a lot of calculus for. But one of the first ways that then we can start like using this math and applying it in real life has to do with being able to take a vector and stop thinking about it in terms of these rectangular coordinates and convert it over to polar coordinates. So what that looks like is this. First, you got to find the magnitude. And we've done this one already, but just like as a quick reminder, Pythagorean theorem. So if it's 3, 4, it's 3, 4. So the arrow looks like this: 3, 4, 3 squared, 4 squared. That's 9 plus 16 equals 25. The square root of 25 is 5. So the magnitude of u is equal to 5. You do those parallel bars on either side to denote magnitude. That's how big this vector is. Now, what about the direction? What is the direction that this vector is pointed in? Okay, well, 3, 4, you can kind of see like it's less than 90 degrees, more than 0 degrees. If I were guessing, it seems like it's pointed a little bit more up, so maybe a little bit more than 45, somewhere in like the 50, 60 range feels right to me. Let's try this out and see what we can figure out. Well, if I'm trying to find this angle right here, one of the things that I notice is I've got a right triangle, and I have the opposite and adjacent side. Which ratio involves opposite and adjacent? I'm thinking, and I'm remembering that tangent does that. So I could do this with lots of different things. I could also use, now that I have the hypotenuse, I could use sine or cosine too. I just find myself using tangent most often. So when I do this, I find that if the tangent of theta is equal to 4 over 3, that's opposite over adjacent, then, well, all I need to do is find out which angle of theta has a tangent of 4 over 3, which I believe is 1.33 repeating. So easiest way to do that is to use your inverse functions, find out what arctangent of 4/3 is. And when I plug that into the calculator, which I did before I started this video, I find out that the angle which has a tangent of 4/3 is 53.13 degrees. You'll find that we use degrees more often than radians here, just because it's helpful to have like the degree symbol, and we're not dealing with like infinite directions. Really, we're only dealing with between 0 and 360 degrees. So the degrees end up being like a more manageable and easy to think about method of dealing with this. You could theoretically render vectors in polar form with radians, but you just won't see it that often, and so I won't encourage that. So then, the way that you can rewrite u using this new information is you can say that u is equal to, and you can do this exact same notation, 5, 53.13 degrees. And the way that you know this is in polar form is because you can clearly see that the second measurement has degrees after it, and so therefore like this must be a rendering of a vector in polar form. We're moving with a power of 5 in a direction of 53.13 degrees.